Hey everyone, it's Mr. N here, and on this worksheet, this was from the 2013 final that I gave. These were the most missed questions, so this is a good review for us to do. It's kind of tight for space on this worksheet, so I'll try to do my best to squeeze everything in here. On this first problem, it says a person whose height is 6 feet is standing away from the base of a straight light along a straight path at a rate 3 feet per second. If the height of the straight light is 20 feet, what is the rate at which the person's shadow is lengthening? So we've got a person here, and we've got this situation going on where we've got that, and oops, I kind of went through his head, so let's just redo that again. There we go. And we've got a shadow that's lengthening here, right there, caused by the street lamp. And this person is 6 feet tall, and they are walking along a straight path at a rate of 3 feet per second. So if I break up these triangles that we have here, we've got two similar triangles. And in this case, I can go ahead and call this my x and that piece my y. And this is the rate at the person is walking. This right here is the person's walking away from the street lamp. So this dx dt is going to be 3 feet per second. Now, this person we know is 6 feet tall, so we could put that 6 right there. And the street lamp is 20, so we could put that there. So this would be 6 right there and 20 right there. And what we end up with here is two right triangles. In our first right triangle, we can say that we've got this as being 20 and this piece as x plus y. And in this one, we've got this piece as being 6 and this as being y. And we can set up a ratio here, and we could say 20 to x plus y equals 6 to y. So I set up that ratio, and if I go ahead and solve this, I could solve this for y in terms of x. So let's go ahead and do that. We're going to cross multiply 20y equals 6 times x plus y. This is a related rates problem, and so what I'm trying to do is I'm trying to find this dx dt so I could substitute that value in, because I'm asked to find at what rate, the rate at which the person's shadow, this, which is my dy dt. That's what I'm looking for. So let's go ahead and finish solving this. I can go ahead and distribute at this point 20y equals 6x plus 6y, and I would end up with 14y equals 6x. So y is going to be 6/14 x. So that means dy dt, at this point, if I take a derivative to find a rate, I'll get 6/14 dx dt. And I know what my dx dt is. They gave me that value as 3. So this ends up being 6/14 times 3. So we end up with 18/14 feet per second, which is 9/7. Let's run out of room. We'll put it right here. This is going to be 18/14. So we said this was 9/7 feet per second, which is my dy dt, and that's the rate at which this shadow right there is changing. All right, let's move on to number 2. A particle moves along a line so that its acceleration for t greater than or equal to 0 is given by that equation, by that function. If the particle's velocity at t equals 0 is 4, what is the velocity of the particle at t equals 5? Well, this one, to find our velocity, let's do another color here. Our velocity is just the integral of the acceleration. So we want to integrate this acceleration on the bounds. They tell me particle at t equals 5. So we want to integrate this from 0 to 5. And we've got the integral of t plus 2 over the square root of t squared plus 1. All right, well, we need to add something into this. At t equals 0, the initial condition is that it's 4. So we need to put in that initial condition. That's important for us to do, because this is our initial value. That's where some of us forget what to do with this. So, since this is a calculator OK question, as noted, you can just completely do this whole thing on your calculator and enter it in, and you will get a value of 12.724, and they don't give me any units, so we'll just say units per time, so we'll just say units per second. Okay, so 12.724 on this one. Again, you could just do this one on your calculator since it indicated that this was a calculator OK portion. All right, let's move on to number 3. It says, let f be a function such that the integral from 8 to 14 of f of 2x dx is 12. So which of the following now must be true? Well, since this is 12, take a look. If I set the bounds and go from 16 to 14, okay, so this is twice that. And we're looking at these bounds right here, 8 to 14. 8 to 14, if you set that up, say, on a number line, you would be going from, let's say, position 8 to position 14, as opposed to if you want to double that right here, it's twice that value, you would go twice that distance. So which of these indicates twice that distance? But remember, for this, you're going to end up with getting twice that area because the integral is the area under the graph. So in this case, we need that 24 when we get rid of that if we're going to double that to keep it balanced. So if we're going to double that and undo it there. So there's a couple different ways of thinking it. So if I say from 8 to 14, this has a difference of 6. From here, 16 to 28, that's 12. That's 12. This is 6, and that's 6. So obviously, if I'm going to change it, it can't be these two. So then I'm looking at these two, and I do need to double this. So the answer is B. This one can be quite complex if you're not thinking of it on the sense of a number line. We did some of these in class, if you remember. So think back to that lesson when we did FTC and areas under the curves and how we break the integrals apart, what the relationship between the integrals are. Okay, moving on to number 4. On number 4, it says the polynomial function f has selected values of its second derivative f double prime given in the table, showing which of the following must be true. F is decreasing on an interval, increasing on an interval, local minimum at x equals 2, the graph of f changes concavity, and the graph of f has an inflection point at x equals 2. So let's take a look and examine this a little bit. Since this is the second derivative, I see that this is f double prime right here, and at 1, at 2, and at 3, I see something happening. At 1 right here, we have a negative value. At 2, we've got a 0. And at 3, we've got a positive value. So, is it increasing or decreasing on the interval? Well, we can't determine that because this is an f double prime. And I don't have enough here to be able to determine it. So I cannot determine this. Take a look here. Is this a local maximum? Well, no, it's not a local maximum because I'm taking a look at the second derivative. So now it's got to be one of these two. Does it change concavity? Well, yes, it does change concavity. It goes from a negative value to a positive value. So yes, it does. So let's hold on to that. And the graph of f has an inflection point at x equals 2. At the actual value, we can't determine if this is an inflection point right there. Cannot determine. So we know that the answer must be D. It does change concavity. We know that for sure. So on this, we know that it changes concavity because this double prime tells me that it's concave down here, concave up there. It does change concavity at the interval. The reason why I can't say that it's for sure a point of inflection, because when we take the second derivative and set this equal to 0, it gives us our possible points of inflection, right? Possible until we test that point exactly there to see what happens. Well, I don't have values in between to see if this is exactly the spot where it does change, right? It's a possible. But I do know that somewhere between 1 and 3, right, on this, because I've got the negative value there and the positive value there, that I do have a change in concavity. Okay, taking a look at the second portion here, and this is a no-calc part, so let's take a look at what we have. And on this first one, it says a function f is defined by this piecewise function. What is the value of the integral from 1 to 6 of f of x dx? So what we need to do for this is we are going to take a look at this right here. This is the border where something happens at 3. So we know that the integral from 1 to 3 plus the integral from 3 to 6 is the full integral from 1 to 6. We can break it apart like that. So on this first one, we're going to say the integral from 1 to 3. And from 1 to 3, this would be for less than 3. I'm looking at this one. So this is 3 dx. Plus the integral from 3 to 6. Now I'm changed, and I'm looking at this graph, this x plus 1 dx. So I can integrate each of those. So for this first one, I get 3x on the bounds from 1 to 3. The second one, I get 1/2 x squared on, plus x. 1/2 x squared plus x on the bounds from 3 to 6. Again, the key was to break this integral apart because of my piecewise function that I have here. So this ends up being 8 plus, and this will be 18 plus 6 minus 9/2 plus 3. And this is going to be 24.5 when all is said and done. Okay. A particle moves along the x-axis with its position t given by x of t equals that, where a and b are constants and a doesn't equal b, for which values of t is the particle at rest. Well, when is it at rest? It's at rest when v of t equals 0. That's when it's at rest. All right, so let's find out. So v of t equals 0. Since I'm given this, I need to find x prime of t. That gives me my v of t. And in this case, we'll end up with first t minus 2a times the derivative of the second, which in this case would be 1. I'm taking the derivative of this with respect to t, right? And then plus the second, which is t minus 2b, right there, times the derivative of the first, which is, again, 1. And remember, this has to be 0. So solving this, I'll end up with 0 equaling t minus 2a plus t minus 2b. So 0 equals 2t minus 2a minus 2b. So a plus b is what my t is. So that is when the particle will be at rest, when a plus b is equal to t. Now, here is a review. How do you find vertical asymptotes and horizontal asymptotes? Well, for vertical asymptotes, vertical, we're going to go ahead and set the denominator equal to 0. So we set the bottom equal to 0. For the horizontal, you can take the limit as x goes to infinity to find those horizontal ones, or we said if it's a rational function, we can go ahead and compare a if it's xm over b xm. If these are the same powers, then it's just going to be a over b. If m is less than n, then y equals 0 will be your horizontal asymptote. If m is greater than n, then you do not have a horizontal asymptote. And again, if m equals n, we take a look at just these, and we'll take the a over b coefficients. So I think that's an easier way to remember. It's a little bit quicker if you just memorize that to work with it. All right, next one. What is the absolute minimum value of this? Well, how do we find the minimum? Well, we're going to go ahead and take this derivative, set it equal to 0, get our critical points, right? And then test these critical points. All right, so f prime of x. Remember, to find absolute, if we're given bounds on this, then we have to test the endpoints of those bounds. So f of x, f prime of x is going to be 1/2 x times 1 over x, so that's the bottom, times the derivative of the top, minus the top, which is ln x times 1/2, over the bottom, which is 1/2 x squared. Cleaning this up a little bit, I'll get 1/2 minus 1/2 ln x all over 1/4 x squared. Setting this equal to 0, basically I need to know where 1/2 equals 1/2 ln x. In other words, where 1 is what ln x is, and this would be where e to the x, in this case, is what I'm solving for, right? So e is what your x value is. So basically you need to test to see at e if it changes. So this is a relative, is what we ended up here, with a relative value from this critical point. And let's see. I get a positive here, a negative there, and it changes from positive to negative, so then I know that it's going to be a maximum. Again, all I did was plug in values for less than e and greater than e. And over here, that means that I want to find f of e, which is ln, I'm looking at this equation now, ln e, because I have to find that value over 1/2 e. Well, that's 1, so I'm just going to end up with 2 over e as my absolute minimum on this one. Or, sorry, my absolute maximum. Okay. dA over dt equals 100 describes what kind of growth? Well, look at, there's nothing going on here with it. I could separate the variables. dA equals 100 dt. This is just simply linear. There's no natural log, there's no exponential, nothing. If you just go ahead and separate the variables and integrate, you get a equals 100t. That's linear. All right, let's move on to the next problem. For number 6, it says, let g be the function given by that, where k is a constant. For what value of k does g have a critical point at x equals 1/2? Well, let's go ahead and on this, let's go ahead and solve and find what g prime of t is. So g prime of t, or sorry, g prime of x, in this case, g prime of x, is going to be first times the derivative of the second, plus first times the derivative of the second is going to be e to the kt times k plus the second e to the kt. Remember, this was the chain rule, right? It was a chain rule. Don't forget about our chain rule. E to the kt times 3x squared. We want to set this equal to 0. So, and then we're going to plug in the point 1/2 at this point. They want to know at x, does it have a critical point at x equals 1/2 for what value of k? So 1/2 is my x. So we're going to go ahead and say 1/2 to the third power e to the k times 1/2 times k plus e to the k times 1/2 times 3 times 1/2 squared. All right, cleaning all this up, we're going to end up with, if I bring this over to the other side, we'll say, we'll just bring this one over, so we're going to say e to the 1/2 k times 3 times 1/4 equals negative, this is where I brought this over, 1/8 e to the 1/2 k. So, cross multiply, solve for k, get rid of the e's, you end up with k. I'm saving space here for you guys, sorry. So you're going to end up having to solve this, and you'll get k equals -6. So that's the value of k where this will work. All right. For t greater than 0, the precision particle moving along an x-axis is given by x of t equals cosine t minus sine t. What is the acceleration of the particle at the point where it's first equal to 0? All right, well, since this is x of t, v of t would be that derivative. So this is going to be negative sine t minus cosine t equals 0. And I'll end up with negative sine t equals cosine t. And I need to do this at t equals, well, let's see, where will those be the same? These are going to be the same if you're looking at your unit circle at two spots, right here and right there. So I need it to be the opposite, so I need the negative sign equal to the cosine, so that would end up being right here. So this would be 3 pi over 4. Again, I chose this because this is where the sine and the cosine are the same value, but in this case they're opposites right there, because one will be, the cosine will be the negative in this case. So looking at this, we get at t equals 3 pi over 4. And if we found the acceleration, we will get negative cosine t plus sine t. And again, we're looking for when they're opposites of each other, when it first equals 0. That's what we're looking for. And again, this will be at t equals 3 pi over 4. Again, think of it as, in this case, you're going to have negative root 2 over 2 plus root 2 over 2, and that'll give you, that'll give you our square root 2 in this case. Okay, so what is the acceleration? The acceleration is square root 2 when we plug that value in. Okay, let g be a function with first derivative given by g prime is equal to the integral from 0 to x of e to the t squared dt. Which of the following must be true on the interval from 0 to 2? Well, let's take a look. If I break this down, I get g double prime. Let's think of what g double prime is. Of x will tell concavity, right? So this will yield concavity. So let's see, is it increasing and the graph is concave up? Is it increasing and the graph is concave down, decreasing, concave up, decreasing, concave down, decreasing, and an inflection point on 0 to 2? Well, g double prime of x is going to be e to the negative x squared times 1. We've got to take the derivative of that, right? Chain rule it. So this is FTC. We took the derivative of an integral, so we got that, times 1. This is, again, by FTC, which yields 1 over e to the x squared. Now, taking a look at this even further, let's see what this gives us. This gives us here 0, there is 2. Those are the bounds I'm looking at. I get positive values in between for that second derivative, so that tells me it's concave up. So I'm looking for the one that's concave up. All right, well, we know, if we put in a test point, we'll have the integral from 0 to 1 of e to the negative t squared dt is greater than 0. This is my derivative, right? This is the original one. So therefore, we know that it's increasing. Since it's increasing and concave up, that's what we're looking for, increasing concave up, the answer is A. Again, what I did here is I thought of it as put a test point in. So put a test point in to see what happens. Well, I put a test point in there. I got it to be greater on these bounds. I got it to be greater than 0. I knew that it was increasing. All right, so let's move on. Here's some more extra practice ones for us to do. So on this first one, it says, using substitution, u equals 3x plus 5. The integral from 0 to 1 of the cube root of 3x plus 5 is equal to what? So let's go ahead and think about this with our substitution rule. Remember, what did I say with our substitution rule here? We can do a little trick. If I put in u of 0, I can change the bounds on the integral without having to resubstitute. So if I know what my substitution rule is, I don't need to resubstitute in the end, and it's evident on look at these answers. They did not resubstitute. Since they did not resubstitute, means you need to change the bounds on those integrals. So we know that u of 0, when I put in 0, I get 5. U of 1. So I'm just taking these two bounds and finding what my new bounds would be if I did not resubstitute. U of 1 would give me 8. So that means my new bounds would be from 5 to 8. And what is my substitution? It's this. U is going to be that. So it's the cube root of u. And this will end up being the cube root of u du d over 3. Because if I take du equals 3 dx, so that means dx is du over 3. So that's where I got that value from. So this can be rewritten as, this is a 1/3 right here. So 1/3, so I could put any constant out in front, from 5 to 8 of the cube root of u. All right, let's see. Do we have one that looks like that? Oh, 1/3 from 5 to 8 of the cube root of u. If you tried any one of these, none of them would work because, again, it did not resubstitute, so you have to change these bounds. All right, taking a look. These are the harder ones on the multiple choice, by the way, and these were the most missed from the final I gave. So that's why we're going over these. That's why some of these may seem a little bit difficult. All right, next one. Find the average value on the interval. Well, this one, average value, is pretty straightforward. Remember, average value is 1 over b minus a times the integral from a to b of your function. So, okay, let's go ahead and do this. This is going to be 1 over 5 minus 0 from the integral of 0 to 5 of our function, which is 4x squared plus 3x minus 1 dx. Well, we can go ahead and finish this off, take the integral, find the answer. We're going to get 1/5. And then here we'll end up with x cubed. This will be 4/3. And then plus 3/2 x squared minus 1 on the bound, 1x, sorry, on the bounds from 0 to 5. So we roughly end up here with 39.83 repeating. Okay. Let R be the region in the quadrant bounded by those two graphs. And for part A, we need to find the area. So this is a little bit more complex. I don't know how much room I have. Let's see if I can move this up and squeeze all this in here. Yes, I can. Let's do that. Okay, so for this first one, we've got y equals square root of x. Looks like that. And y equals x minus, or x over 2, so that's going to give me a line that looks like this. So I've got this kind of situation here, and these intersect. If you set the square root of x equal to x over 2, that's going to have to be at 4. You can kind of intuitively look at that and figure that part out. So we need to, in part A, find the area. So for part A, we know that the area is the integral of the graph from 0 to 4, and this is going to be the top curve, square root of x, minus the bottom curve, which is x over 2 dx. We can go ahead and find this area, and that's going to be 2/3. We'll take the integral, x to the 3/2 minus 1/4 x squared on the bounds from 0 to 4. plug those in, and you'll get A equals 2/3 4 to the 3 halves minus 4 to 3 halves minus 1/4 to the 6 1/4 times 16, and you'll get the area as being 16/3 minus 4, which gives you 4/3 square units. All right, for part B, it says find the volume of solid generated when R is rotated about a horizontal line y equals 1. So we're going to rotate this region about a horizontal line y equals -1. So that line will be down here, and we're going to rotate it like that. So we want our slices to be perpendicular to the axis of rotation, so that's going to give me slices that are going to be dx. So the volume is going to be pi times the integral from 0 to 4 of r squared minus little r squared dx. Now, in this case, we need our big R to be minus -1, and our little r minus -1, because we're going to subtract, since it's below, we're going to say r minus the line of rotation. R minus the line of rotation. Big R, little r minus the line of rotation. So that's why I set that up like that. So the volume will be pi times the integral from 0 to 4, and this will end up being the square root of x plus 1, this big R squared, minus my little r, which is x over 2, plus 1 minus -1, remember that, and dx right there. Okay, we can, at this point, you could go ahead and use a calculator at this point, and we'll end up with 5.33 pi, or we'll say 16 pi over 3 cubic units. Okay, for part C, find the volume on its rotated vertical line, x equals -1. So this time we've got a vertical line at x equals -1 right there, and we're going this way. Take our slices to be perpendicular to the axis of rotation. This time I need dy. So I can solve this. So y equals x. So in other words, since I need dy, I need my equations to be in terms of y. So x equals y squared, and 2y is x. So I solved each one of these up here. All right, so now in this case, the volume is going to be pi. And now I need to know where it intersects up here, and that's going to be at 2. Okay, since this is 4, you could just plug it in and find that. All right, so they intersect at 2 in the y. So this is going to be from 0 to 2, because my slices are going all the way up to the 2. And this time I'm going to say the left curve, or the right curve minus the right curve, is going to be my big R. So in this case, it'll be 2y. This is my 2y equation. So 2y minus my line of rotation, so plus 1, minus -1 squared. So this is my big R squared. In other words, this was big R minus -1 again, squared. So now we have to subtract out little r, so y minus -1, so that'll be y plus 1 squared like that. dy, again, we're going to use a calculator at this point, so we will end up with 6.93 pi, which is 104 over 15 pi cubic units. All right, for part C, or for part D, sorry. For part D, we are looking at this. The region R is the base of solid. For this solid, the cross sections perpendicular to the x-axis are squares. So cross-sectional area is what we're looking at here. So we've got this, again, graph, and then perpendicular to the x-axis. So these are squares coming out at you like this. So squares will come out at you, out of the board, out of the video, to you, smacking you in the face. So since we are looking at squares, we know that it's side squared. That's an area of a square. So that means we want the volume to be the integral of the area, and here it is. Well, what's the side of the square? Well, this side is going to be the top curve minus the bottom curve. So that's going to be the length of my side. So the volume is going to be the integral from 0 to 4. So these are all my squares coming out like this, and it's going to be the square root of x minus this x over 2 squared. That and dx right there, this is my squares, again, that are coming out, smacking you in the face. That's the length of each side of them. So we can go ahead and use our calculators at this point. So we end up with the volume equaling 0.53, which is 8/15ths. And this is cubic units again. All right, let's look at part E. This time we've got the same situation, but the cross sections perpendicular to the y-axes are squares. Okay, so this time, same thing going on. I've got this curve right there, looks like that, and I need to go up to 2 though, because they're coming out this way. Again, these are coming out this way now. These squares come out right out, you smacking you in the face this way instead of the other way, because perpendicular to the y-axis. So all these little black marks are squares coming out of the board. Okay, so now in this case we've got the volume is the integral of the area, same thing, side squared. So we're going to deal with 0 to 2. This time I need the right curve minus the left curve, and I need it to be in terms of y, just like we did over here. So this will be 2y minus y squared dy. So solving this, we can go ahead and use our calculators at this point, and we will end up with the volume being equal to let's see, this comes out to be 1.067, so we're going to say 16/15ths cubic units. So the volume was the integral of that area. We went ahead and set it up, solved it, and that's what we got. So hopefully this review helps a little bit, and again, this was in 2013, the final I gave. These were the most missed questions. These were the toughest for them, so hopefully this helps you. All right, good luck.